Hi everyone. So we will be discussing chapter 2 atoms for today, and we'll start about the classification of matter. Okay, and let's start with matter, defining matter. Matter is anything that occupies space and has mass. So it's basic knowledge in our chemistry that I know most of you have already encountered in your introduction or early years in studying chemistry. So matter is also divided into two, which is pure substances and mixtures. And Okay, when we say pure substances, it is fixed composition and cannot be further purified, while mixture is a combination of two or more pure substances. So, um, pure substances can also be divided into two. Say, for example, we have elements and our compounds. So, when we say elements, they cannot be subdivided by chemicals or physical means. So, if we have periodic table, say Okay, so I have this one right here. This periodic table is the one that I've been using. This is not sponsored in any form, but this is um, periodic table. You can download it in your app store. And when we say elements, the following here, listed here in your periodic table, are all considered as elements, okay? So they cannot be divided by chemical or physical mean, okay? So um, a combination of elements will form your compounds, and compounds are elements united at a fixed ratio. So it cannot be a half of this element, it should be a whole element. So we cannot say that one half of hydrogen and one half of magnesium. So we must say, meaning ng fixed ratio is you have one hydrogen or two magnesium or three uh, titanium kung alin man doon. Okay? So we have your mixture as well, which is a combination of two or more pure substances. So when we say mixture, it is also divided into homogeneous matter and heterogeneous matter. So homogeneous matter are uniform composition or have uniform composition all throughout. While heterogeneous matter, they are non-uniform and composition. The common question that I've been asking my students about mixture is the example blood. Now, if we're going to see blood as it is, now we're not going to look at it inside the microscope. We can consider it as homogeneous because it has uniform composition that our eyes can see. But when we dive deeper, no, or we see it on a microscopic perspective, we know that blood contains platelet, it contains WBC, RBC, no, and other chemical components. So we considered blood as heterogeneous matter. Okay. Okay. Okay, so compound is a pure substance that is made up of two or more elements in a fixed ratio mass. And formula of compound tells us the ratio of its constituent element and identifies each element by its atomic symbol. So, is it necessary for us to memorize the periodic table? And some professors, some university requires that, but um, that's not necessary for us to memorize. The important thing to know in your periodic table as we go by, since this is just an inorganic chemistry, um, on your organic chemistry, the most important elements should be familiarized, such as this carbon. You know that it is six. You know that um, the number of protons is six, the electron is six, neutron is six, or its weight is 12. No? You'll get used to it eventually. But is it important for us to memorize everything like hafnium, tantalum, tungsten, rhenium, osmium? Now, on some we should familiarize on the shorthand writing of it, but on really diving deeper on this chemical component is not necessary in this subject only in inorganic and organic, but it's very helpful it's very helpful for us to understand not just the properties of this chemical component, but to dive deeper on its arrangement in this periodic table and its trend, no, its chemical trend. It's very important. So the formula compound, it tells us the ratio of its constituent element and identifies each element by its atomic symbol. So when we say sodium chloride, that means we have 1:1 ratio of your sodium, which is yung Na, we're gonna look at when we're gonna look at it here in periodic table. Sodium, which is Na, contains one right here. Now, if it's one, um, we can not write. Okay, if it's one, it's okay for us to not write number one. And then our chlorine, which is also one, it's right here. So this one is also one. Now, if you don't see any number or a subscript to it, it means it has only one. Okay, so the ratio of sodium atom to chlorine atom is 1 is to 1. How about this one? We have H2O, that means we have two element hydrogen and we have one hydrogen right here. That's why the ratio for this one is 2 is to 1. But what if we see something like this one? 2, okay? So this means that we have two compound or um, two compound of sodium chloride. No? So if we're going to count how many sodium or how many chloride do we have in this formula, then we'll just need to distribute number 2, no, on our subscript. So we will just be multiplying it to its subscript. So that will be sodium will be 2 and your chloride will be 2. So another thing, can we let's simplify. Say for example, we have two molecules of H2O. That means how many hydrogen atom do we have in this equation or in this formulation? Then we'll just have to multiply 2 to its subscript. So that will be 4 hydrogen and 2 times, since we don't have subscript right here, and it is given that it is 1. So that will be 2 atoms of oxygen. So the ratio for your hydrogen to oxygen is 4 is to 2. Or we can just simplify that. No? We can just simplify that to its base formula, which is 2 is to 1. Okay? Okay, so when we say element, it is a substance, for example, carbon, hydrogen, iron, so that consists of identical atoms. So there are 118 known elements of this. 98 occurs in nature and the others have been made by the chemist and or physicist. So their symbol consists of one or two characters as you go through this periodic table. And the names are derived from the variety of sources. The English name of the element, some know, is derived from geographic location, planets such as Mercury, atomic science, mythological creature, and more. So this is a water molecule. So we have different ways of representing our water molecules. So we have this number one right here, molecular formula. No? If we see it as the elemental shorthand writing, which is H instead of hydrogen, we have the subscript to note how many hydrogen is there in the molecule, and then the other atom right here. So this is molecular formula. If you see lines drawn, which is commonly may encounter here, you'll encounter that on your organic chemistry. You'll see line to indicate if it's single bond, double bond, or triple bond. So when we say line right here, it means it is connected, no? Or they are sharing, no? They are sharing an atom, no, to sorry, they are sharing an electron, ano, for them to be bonded to one another. So this one, if you see line right here or a line right here, it can be single or double or triple. You know, this is your structural formula. And as I've said, you'll encounter more of this in your organic chemistry. So this one here is your ball and stick model. So each element is represented by different colored ball, no, and this is usually the one that is requested by the professor as an assignment, the ball and stick model. So maybe you'll encounter that in your professors. But this one is a ball and stick model. It shows the angle, it shows the bond of the molecule, and it shows the size of the molecule. So as you'll notice, no, this one is your hydrogen, small, and this one is your oxygen. No, the size that the atomic size, no, will be understood further, no, sa ating mga periodic trends, no. But if you'll notice, the size of your hydrogen is just 1.0 1.008 gram per mole. Now, while your oxygen, because it contains more protons than your hydrogen, it's heavier. So the size is bigger as well. So we also have this space filling model. It does not show any bond, but it just shows the size, no, and how the molecules is connected to the main atom. Okay, so this one shows the relative size of your hydrogen and oxygen in the water molecule. Okay. Right. Okay, so a mixture, no, is a combination of two or more pure substances. So the substance may be present in any mass ratio, and each substance has a different set of physical property. Mixture may be homogeneous and heterogeneous, as we have discussed just a while ago. And if we know the physical properties of an individual component of the mixture, we can use appropriate physical means to separate the mixture to its component parts. So let's head forward to our Dalton's atomic theory. So John Dalton um, theorized that all matter is composed of a very tiny particles we call an atom. Okay, so and all atoms of the same element have the same chemical property. Say, for example, the same element carbon that is found on charcoal, say, for example, has the same chemical property as those that can be found in the diamond. No? So atoms of different elements have different chemical property. The hydrogen or the water molecule that can be found in your orange juice is the same as the water molecule that can be found in your plain water because it just contains a hydrogen molecule. And all hydrogen molecule, no matter its form as a mixture, it will still and will always contain 1.008 gram per mole and the same amount of proton, electrons, and our neutrons. Okay, so atoms of different element have different chemical properties. So of course, hydrogen is different from lithium. Lithium is different from sodium, and so on. So compounds are formed by chemical combination of two or more of the same or different kinds of atoms, and molecules are a tightly bound combination of two or more atoms that acts as a single unit. Take note, tightly bound combination. So compounds are formed by a chemical combination of two or more or same or different kinds of atoms. Okay. Okay, so we have this law of conservation of mass, again by John Dalton. Matter can be neither created nor destroyed. I'm sure you have heard of this many times, not just in chemistry, but also on other subjects. So matter can be neither created nor destroyed. No, it can only be transferred to one form and to a form, um, to one form and another. So as Dalton explained, if matter is made up of indestructible atoms, then any chemical reaction just change the statements among atoms but does not destroy the atom itself. So dito sa ating formulation na ito or dito sa on this statement, okay? On this statement, we can craft a equation that will just shows that we have right here this one. These are the reactants, okay, or the elements or the formula or the mixture that we use initially, and these ones are our products. Okay, always remember this from this law of conservation of mass. Okay, if carbon right here is just one, carbon on your product should also be one. No, this is uh, the very famous balancing of equations, no, for sure na aaralin natin. We'll study that in the future, but then let's focus right here. If the carbon right here on our reactant side, no, is just one, the carbon right here should also be one because it cannot be created nor destroyed. It will just be transformed to another form. The oxygen right here is one and two. Now, on our product side, once it has been transformed, it should also be 1, 2. Okay? For your lead, no, we have one right here. It should be one right here as well. Okay? So, as you may notice, the oxygen has a high affinity to our carbon monoxide. That's why it will be absorbed or it will connect its bond to our carbon right here. No, and our lead, no, will be a metal. No, when we say metal, they are inert. Um, they are not easily activated, no? And this one, no, this lead is a metal. Okay, so we'll discuss further on that. What's important is you understand that matter cannot be created nor destroyed. You can't add another lead right here, another oxygen right here. If in your reactant there is no additional, unless you are doing an experiment and this whole equation already take place on this. Say, for example, you have this beaker, you added carbon monoxide and lead oxide right here, no? And then it reacted and it showed this product, carbon dioxide and lead. And then you realize that maybe you wanted to add more lead oxide, then the whole equation will change, okay? Or it will just saturate the whole solution. But nonetheless, no, we'll discuss this further. What's important is matter cannot be created nor destroyed, and you understand that what you exert is what you will also receive on your product. No? Okay, so we have law of conservation of mass. Take note of this: monoatomic elements. We have diatomic elements and polyatomic elements. Well, from its name, they should be monoatomic elements, consist of single atoms like helium, neon, meaning these are gases, no? They can exist, no? These are inert gas usually. Helium, neon, argon, krypton, these are inert gas, no? In our octet rule, their shell is already filled, meaning they do not react that easily, no? Unless subjected in a very high pressure. These inert gases doesn't act that easily when combined with other element because they are already completed, no? They are already completed. Hindi sila mabilis mag-react kahit kanino. Kasi kumpleto na sila. Okay, this might sound like an advice in life, but when these inert gases, they are inert for some reason, meaning they can exist, no, in nature as a single element without reacting, no, to other elements, no, present in nature. So we also have our diatomic elements, meaning they cannot exist in our environment, no, alone. So they should be in pair. So you have to memorize this one. If it's helpful for you, you can create a mnemonics from this. My classmate says Brinkelhoff. Let me check if that's really working. Brin, it's not working. It's not working for me. The mnemonic side, but my classmate tells me always that you can use Brinkelhoff. I don't know how. Okay, Hoff. Brin, chlorine, Hoff. I don't know if you would remember that, but it works. No, it works for me. My classmate always tells me that, and it works for me to remember just the atomic elements. Brinkelhoff. So we also have polyatomic elements, meaning they exist in nature, not just one, but also two or more elements. No, so O3 or yung ating ozone, we have the P4 and we have yung S8. So diamond has millions of carbon atoms bonded together to form one gigantic cluster. So even if it is a diamond, it has a very strong bond within each other. It is still a carbon. What you can, as I've said, what you can found in your charcoal, in your body, no, is the same carbon that can be found in diamonds. Only that the bonds, no, is different. The way it is created is different. Okay, so these are the subatomic particles as said by Dalton. Ano? So we have proton, electron, and neutron. So proton, it's easy to remember, P for positive. This one's a positively charged molecule, and its mass, remember, is 1.6726 times 10 raised to negative 23. The atomic mass unit is 1.0073, and the mass, no, if rounded off, is 1. So it can be found in the nucleus. So remember, okay, we have a positive proton inside the nucleus, and we also have the neutron inside the nucleus. Now the neutron is zero charge, or it is not a charged particle, okay? So we also have your proton right here. So this one is your nucleus. This is the nucleus or the center point of every atom. No matter what element it is, they always have proton, they always have neutron and an electron. They always have electron, proton, and neutron. Okay? So remember, no matter element it is. Okay, where was it? Okay, we have 42, 42, 54. But where is our electron located? It can be found in the outside part of your nucleus. So we have this called an electron cloud. No, this is just how I show it. Okay, and this electron cloud usually have electrons right there. It creates negativity that surrounds your atom. So it creates negative charge, no? And when two element is connected by bonds, no, they always connect, of course, with the outside area of your nucleus, which is your electron. So when we talk about bonding, when we talk about connecting two elements, we are talking about the electron on its electron cloud connecting to another, connecting itself to another atom that has the same electron cloud, okay, or different electron number. Okay, so the electron is very important when we consider bonding. Okay, that will be discussed further. But remember that this is negatively charged particle, no, and you'll notice that the weight of an electron is too low to a point that it doesn't add a weight, no, on every atom. So, saan manggagaling yung weight, no? Where are we going to look for the weight of every atom? So, we have this proton and our neutron because both of them have mass. Okay, our electron has mass as well, but it is too low that it doesn't add any mass. So, on how many number, say for example, I have 42 proton, what is the mass of that 42 proton? So that would also be 1 atomic mass unit. So let me give you an example. Our sodium right here contains 11 electrons, 11 protons, and 12 neutrons. So if I'm going to compute for its atomic mass, no, I have to compute for your proton plus neutron. So in that case, this is 20, 23 point something. No? Since this one is a rounded off, bakit hindi ma'am 23? Why it's not 23? Because we have this additional numbers right here. Now we're just rounding it off. So if we are going to round off this weight, it is also 23. So it's one significant figure, right? So our electron doesn't have a bearing into the weight of our atom. So the proton and the neutron is responsible for your weight. Okay? So the weight is mainly found on the nucleus of our atom. So the unit of mass is given in atomic mass unit or what we call AMU. So 1 AMU is defined as the mass of an atom of carbon with 6 protons and 6 neutrons. Let's head back to the example carbon that has 6. Um, okay, the mass is 12. If we're going to look at the protons and neutrons, these are both 6. So 6 plus 6 is 12. So the mass of our carbon is 12.0106 gram per mole or AMU. Okay, so 1 atomic mass unit is equivalent to 1.6605 times 10 raised to negative 24 grams. Okay. Okay, so knowing this last statement, the one atomic mass unit is defined as the mass of an atom of carbon with 6 proton or the isotope of carbon with 6 proton and 6 neutron in the nucleus. So that will mean that uh, the conversion factor for one atomic mass unit is 1.6605 times 10 raised to negative 24 as it is based on the um, carbon mass because it is one of the most common occurring element, no, in our environment. So you have one atomic mass unit now is 1.6605 times 10 raised to negative 24. So this is a typical atom. Okay, so this one is a relative size of atomic nucleus and an atom, as we have discussed just a while ago, but for drawing, I'm sorry about that. This one is a typical atom example. So in the middle, we have our nucleus that contains our proton, represented by the red ones, and the neutron, represented by the blue ones. And you will notice that there will be an electron cloud, no, represented by the blue color that surrounds the nucleus, and this space is occupied by the electron that continuously move around, its electron cloud. Okay, so we'll head to our discussion of mass and atomic number. Okay, so when we say mass number, this is the sum of the number of protons and neutrons in the nucleus of an atom. So you'll just going to add your protons and neutron, then you'll get your mass number, just like what we have done just a while ago. No? So the mass of an electron is an atom is so small. This is what I've told just a while ago. Din po. And the mass of an electrons in an atom is so small compared to that of its proton and neutron that electrons are not counted in determining the mass. As you will notice, our electron has 0.0005 mass, and this is all already rounded off to one significant figure. That's why it's not that significant when added. So an atomic number, however, on the other end, are the number of protons in the nucleus of an atom. So if you're going to see a typical periodic table, not a periodic table in online, the one that is printed out, no, you'll notice that you have a subscript and superscript. Now you have the subscript and the superscript on the left side of your element, but it varies, and it varies from the copy that you'll obtain of this periodic table. But this is the standard one, and you'll notice that you have this superscript 12 on your carbon, which is your mass number. Remember, mass is always above. Okay. Okay, and your atomic number is below. So mass number is the number or the sum of your proton and neutron. The atomic number is just the number of your proton. And then we have your symbols of element, which is C for carbon. So take note on some exams, no, some may ask for you to count or compute for the number of neutrons given the mass number and atomic number. So it will be easy as long as you know what contains the mass number. So you're just going to subtract your mass number to your atomic number, and then you'll find your neutron. Okay? Okay. So it's easy to look for other element. As much as you know the mass number and atomic number. Say for example in nitrogen, the one that can be found as a superscript in this application is your atomic number. So number 7 is the number of your proton. So that is your atomic number because it is the number of your proton. Remember that. Now let's give another example. Magnesium. Magnesium has 12 right here. So you have 12 right here. And then you have 12 proton. That means your atomic number is equivalent to your proton number. Okay, and then no, your neutron can be found. Sorry, your neutron can be found if you subtract your mass number to your atomic number. I'm sorry, I have no other space, but remember as well that mass number is equivalent to the sum of your proton or your positively charged particle plus your neutron or your neutral particle. Okay, and then we have this so-called isotope. So what is isotope? From its name, iso. Now, atoms with the same number of protons but different number of neutrons. Okay, that means, okay, remember atom. So let's grab the classic example, carbon. Now, they have the same number of protons, but different number of electrons. Of neutrons. Okay. The most common occurring isotope of carbon, okay, is the carbon that contains equal number of proton and neutron. So this is carbon 12. Okay, but in our environment, there's a lot of isotopes or different version of that carbon that is reoccurring. However, we just pick one, no? We just pick one isotope that is commonly occurring in nature. Now, on the other hand, some compute for its weight, okay, like this one, the atomic weight for every isotope. But let's move forward on that later. But as you may notice, there are version of carbon that has 6 proton but 7 neutron. So if you're going to add that, it would be 13, and we call that carbon 13. We have those that have 6 proton but different neutron. If you have 8 neutron, if we add that, that would be 14. That's why it's called carbon 14. So most elements found on Earth are mixture of isotopes like chlorine. Chlorine is 75.77% chlorine 35 and 24.23% chlorine 37. So remember that isotope, we have same number of protons but different number in neutron. We call it isotope. So how would we compute for the atomic weight of the isotopes if we have different number of neutrons? Remember, neutron has one rounded off to its one significant figure, has one um, 1 gram per mole weight, and proton also is 1 gram per mole weight. So there's no problem in proton since on our isotope we have the same number of protons. The main problem is our neutrons, and our atomic weight is computed together with neutrons, not just protons, correct? So atomic weight, the weighted average of the masses in atomic mass unit of the naturally occurring isotope of an element. Example. Okay, we have this example. Chlorine is 75.77% chlorine 35 and 24.23% chlorine 37. So this both version of our chlorine is commonly occurring in our environment. So we have to know the atomic weight that we'll be using in our periodic table for uniformity. So what they've done, is we have our percentage, which is 75.77 divided by 100 for its percentage, multiplied by the 34.97 AMU, or atomic mass unit weight of the chlorine 35. We also have this 24%, 0.23 divided by 100 to remove the percentage, multiplied by the atomic mass unit of chlorine 37, which is 36.97. So in totality, the sum would be 35.45. So hence, the chlorine atomic weight that can be found in your periodic table is 35.4521. Okay, so atomic weight in the periodic table is given to 4 decimal places using more precise data than given. Why are we doing this? It's for uniformity, so that whenever we conduct an experiment or we do experiment from different parts of the world, no, we have a similar result that we will be having. Okay, so the mass and size of an atom, considered an atom lead-208, so that is Pb, no? It came from why Pb? Why is it Pb even if it's lead? It came from its Latin name, plumbum. Okay, where is that? Okay, so here is your lead, number 82. So we have 208. So consider an atom of lead 208. A lead 208 atom has 82 protons, 82 electrons, correct? And 200, 126 neutrons. So let's say this is an isotope of our lead, right? Because lead right here, our typical lead, or the one that is in your periodic table, is 125. Okay, that makes sense because as we have understand previously in the isotopes, we add the number of protons and neutrons right here. And if we add 82 plus 125, that's 207. So this one, the lead 208 that is mentioned here on this example is an isotope. Okay, so the mass of the lead 208 atom is 3.5 times 10 raised to negative 22, and that is given. It requires what you will not go on your laboratory and compute for the mass. You will not measure the mass of your lead atom. Okay, but there are easy way to do it. No, that just need a lot of formula. It just needs formula that we may be we might discuss in the future. So it requires 1.3 times 10 raised to 24 atoms of lead 208 to make 1 pound. So the diameter of lead is, these are just some examples, is 3.1 times 10 raised to negative 10. Virtually all of the mass of an atom is concentrated in its nucleus. Now we know that already because the nucleus contains the protons and the neutrons. And the diameter of the lead 208 nucleus is 1.6 times 10 raised to negative 14. Its density is of a lead 208 is 1.6 times 10 raised to 14 gram per cubic centimeter. So these are just some nice to know facts and how we estimate the size of an atom, the mass of an atom, how we write it in a clear manner. But number two, we'll move forward to our periodic table, the star of this topic. So this is created, no, and arranged by Dmitri Mendeleev. No, there are a lot, or there are various spelling of Dimitri's surname, so you may want to refer to your textbook, the one that is your reference, to avoid mistake in your exams. So Dmitri Mendeleev, no, arranged the known element in order of increasing atomic weight, beginning with hydrogen. Now notice that hydrogen is on the topmost layer, no, of your group 1. Can you observe that when an element are arranged in this manner, certain sets of properties recur periodically. So this is what I call trend. No? This is what we will understand later, or we will create an easy way for us to understand the trend. Okay? So certain sets of properties recur periodically. He then arranged elements with recurring sets of properties in the same column. It's the vertical row. So this one are the column. Maybe you are seeing this heart-shaped pointer that I'm using. And lithium, sodium, and potassium, for example, falls in the same column. Okay, where is that? Lithium, sodium, and potassium. They fall on the same column 1. Also, for example, uh, in the same column and start a new period, no, which is the horizontal row. So periods are the horizontal rows. This one. And remember, columns is the vertical row. Well, columns is always vertical, even in Excel, even in the Greek, no, in the Greek buildings, what the long parang foundation of the walls, they are called columns, right? So anyway, not important, but columns are always vertical, periods are the horizontal ones. So these are the four halogens, no? So chlorines, gas, bromines is a liquid, and iodine is a solid. This one are the halogens, no? Chlorine, bromine, iodine, astatine, and tennessine. Now these are, again, chlorine and chlorine are gases, but they have a solid form, but they are um, not as an element as in itself. Now, bromine is a liquid and iodine is solid. Okay? Okay, so these are the classification of our periodic table elements. Now, the red ones are the metals. The blue ones are the metalloids. They are metals, but they are acting as non-metals, or non-metals and acting as a metal. So they have both characteristic of metals and non-metals. The green one, no, are can be found on the right side of your periodic table, facing it, no. Aside from our hydrogen, so hydrogen is a non-metal. Remember that, no. And we have the lanthanides and the actinides at the bottom part of your periodic table. Okay? So when we say metals, you know this for sure. You've encountered metals all around you. They're solid at room temperature. We know that, right? The nails that is holding your chairs, that is a metal. And they are solid at room temperature. Hindi naman sila nagme-melt, no, at room temperature, except for mercury. So mercury is a liquid at room temperature. They are characteristic of metal. They are shiny. They conduct electricity. You know that because copper is the one that is powering, no, your cell phones. No, there's a lot of copper in that, and other materials. They conduct electricity. The copper wire that holds um, the the electricity wire. What do you call that? The wire that we use in every electrical circuit we have. So they are also ductile and malleable. They can be bent. No, there are other forms of metals. We call them alloys, and alloys is a combination of two or more metals. So brass is an example of your alloy. These are formed by copper and zinc. Your coins that we use in paying the coins, they are also an alloy. So in chemical reaction, they tend to give up electron. Remember metals, okay? Metals are electron donor. Electron donor. They give up electron, okay? Okay, so we also have your non-metals. Except for hydrogen, they lie on the right side, as I've said, no? This one, hydrogen, is on your left side. And except for graphite, remember the except for graphite, they do not conduct electricity. And in chemical reaction, they tend to accept electron. Okay? So these nonmetals are the electron acceptor. Remember that. Okay, so we also have your metalloids, and they have some of the properties of the metals and some of the non-metals. So for example, they are shiny like metals, but unlike metals, they do not conduct electricity. So there are six elements that are classified as metalloid. You may want to create another mnemonics for this one. I don't have one, but you can create one. We have boron, silicon, germanium, arsenic, antimony, and your tellurium. So one of the metalloids, silicon, is a semiconductor. So it does not conduct electricity under certain applied voltages, but it becomes a conductor at a higher applied voltage. Okay, so for our periodicity, this is the trend that I'm talking about, and these are the patterns that the periodic table are exhibiting. So we'll discuss some on this end, on this part. Okay, so right here we'll see the halogen group, that's 7A elements. Okay. These are your fluorine, chlorine, bromine, iodine, and acetylene. So it's right here next to your inert metal, inert gases, the helium neon, or inert elements. We have fluorine, chlorine, bromine, iodine, and acetylene. So as you may notice, the boiling point decreases, no? As it goes down. So that's one example of the periodicity. That's an observed pattern that is um, seen in our periodic table. So another one is the alkali metal group 1A, which is right here, this column 1. These are the lithium metal, so that doesn't include our hydrogen, because hydrogen is a non-metal that is just included in this column. So we have your lithium, sodium, potassium, rubidium, cesium. Okay, and you'll notice that the melting and boiling point goes up, no, starting from the bottom up to lithium. Okay, so another one is your noble gases, which is group 8A elements. And these are your helium. This is in the very right corner of your periodic table. These are the noble gases, or the inert elements. We have the helium, neon, argon, krypton, xenon, radon. No? The melting point of this is decreasing as it goes down the periodic table. So we'll discuss further our periodicity, especially up until the end of discussion. We'll have the electronegativity, and also the electron affinity, the atomic sizes. But before we go on to that, we'll discuss first the electron configuration. So when we say electron configuration, this is the arrangement of electrons in the extranuclear space. So the energy of electrons in an atom is quantized, which means that an electron in an atom can have only certain allowed energy. So we have the ground state electron configuration, which is the electron configuration of the lowest energy state of atom. So before we move forward our discussion, let's discuss first, the electron configuration and the distribution of the electron shell. Okay, so before we discuss this, the distribution of electron in shells, I would like to first introduce the electron configuration that we are talking about right here. So if you're going to search your own electron configuration, you can just go on Google, find electron configuration, and look for image, and you will see this same structure that I'll be putting here in my notepad. So, however, it might be a more rotate ones, because most of what I've searched on Google are different orientation than this one, but it is still the same. Okay, I would just like to give this formatting to you, apart from what you will learn from Google or your professor, or maybe your professor has a different way of understanding electron configuration. But okay, let's start with this one. So the first thing to do is you're going to write the number up to 7. So that is 1, 2, 3, 4, 5, 6, 7. I'll repeat that, but this time start with 2, 3, 4, 5, 6, and 7. And then start with 3, 4, 5, 6, 7. then 4, 5, 6, and 7. Okay, so once you have written this one, remember that we have spdf configuration, which might sound complicated, especially if I'm introducing electron configuration first before that shells that we have on our previous slide. But I want you to just remember S, P, D, and F. So these are different orbitals that can be found in a shell. But remember that S is for sphere, so its shape is more of a spherical orbital. Your P is more of a dumbbell shape. Your D is more of a clover shape orbit. And your F is somewhat have a complicated type of orbital, but however, or a deformed one. But you have this one, the S1 can contain 2 electrons. Remember that? Your P1 can contain 6 electrons, and your D1 can contain 10 electrons. Your F1 can contain 14 electrons. Okay, so what is it's important for our electron configuration? So you're going to write on the first period, or on the first row, you're going to write S. This is for you to be able to draw your electron configuration without any copy, or for you to better understand it. While some periodic table, the printed ones, can give you a copy, a clear copy of how periodic table, how electron configuration works. But I'm just drawing it out so that you'll remember them even without that copy. Okay. So the next one is P, then your D, then your F. Okay. If you're a Filipino watcher of this chemistry subject, maybe you have encountered the mnemonics already. But if you're not, you can create one. But it's easy to understand. Now, some use arrows to understand them better. An arrow such as this one, like this one. Okay, but I have a mnemonics for those people or those students, the Filipino student watching this. This might come a little bit off, but this is how I remember it from my uh, elementary class before, or sorry, high school class before. So, si Susan pumasok sa pinto, si Daddy pumasok sa dilim. Paano si Freddy Daddy? Paano si... Okay, okay. Paano si Freddy Daddy? Paano Freddy Daddy Freddy? Okay, so that exact combination, I'm sorry if you didn't read that. Um, okay, let me repeat that mnemonic once again. No? Si Susan pumasok sa pinto. Si Daddy pumasok sa dilim. Paano si Freddy Daddy? Paano si Freddy Daddy? Paano Freddy Daddy Freddy? I don't know if you would remember that, but on my case, some of my students also create their own mnemonics like shoot, panchito. I don't know if you would remember that. So you might as well create your own mnemonics. Okay, so this is just an example of your electron configuration. And this will be discussed further how to be able to use it on the next video, or on the next, no, not on the next video, but on the next slide. Okay, so let's head back to this. You have a brief just an overview of your electron configuration. No? Now let's move forward to your shell. So this is the distribution of your electrons in shell. So shell 1, 2, 3, and 4. So as you notice, on your shell 1, you have 2 electrons, so it can hold 2 electrons. On your shell 2, it can hold 8 electrons. On your shell 4, it can hold 18 electrons. And on your shell 4, it can hold 32 electrons. Okay, so this short summary is just to show you that the relative energy of electron in each shell go higher, no, as we go further on each shell. So that means the relative energy is also directly, or have direct relationship with the number of electron that one shell can hold, or with the number of electron. So of course electron gives the negative um, negative negative charge. So on this table 2.6, now this is just a distribution of your orbital within the shell. So for every shell, we have this called orbitals, and these orbitals are the four orbitals that I have discussed on this separate sheet. And for each shell, remember that it contains this orbital. So if you'll notice on your shell 1, no, we have just your S. No, we have just your S. So on this part, this is just your per shell orbital. Okay. On your second orbital, we have 2s and 3p. If you're going to notice this next orbital, we have your 2s and 2p orbital. Okay, this is your shell 2, right? And for your third shell, we have 3s, 3p, and 3d orbital. So that is, hold on, okay, this is your third shell orbital. Oops, doesn't, okay, we have your third shell orbital. Okay, and for your fourth shell orbital, we have the 4s, 4p, 4d, and 7, 4f orbital. That will be this one. Okay, so and so on and so forth. So this is just a distribution just to show you how you will compute the number of electron that one shell can hold through each orbital that it contains. Okay, for your first shell orbital, this one, we have one s orbital. So we understand that when it is s, we have how many electron? Two electron can fit this per shell. So we have right here two electron. Okay. Okay. And that means on your first shell orbital, we can fit in a maximum of 2 electron right here. Okay. I hope you are following. Number 2 or your second shell can fit in. You have this s orbital. This one. These are orbitals. Remember it. This one is an orbitals. Okay. And one shell can contain more than one orbital. Okay. Like this one. This second shell or second shell. This is your first shell. This is your second shell. This one is your third shell. This one is your fourth one. Fourth, fourth shell. Okay, and the rest goes on. So for your second shell, we have two orbital inside it. Okay, so for your second shell, you'll notice that we have two s. Remember, we have two s and we have two p. So we have two electron for your s, two electron for your S, and then six electron for your P. So that is a total of 8 electron. Thus, it is shown in this PowerPoint slide that we have 8 maximum number of electron shell in this shell number 2. Okay, and for your shell number 3, we have 3s, 3p, and 3d. And as you may notice, we have 1 for your sphere, that means 2 electron can fit in on your s. We have 3p, that means we have 6 electron. We have 3d, which means you can fit in 10 electron on that end. So this is a total of 18 electrons. So this is 18 electron. Okay, in the fourth shell, we have this 4s, 4p, 4d, and also for F. So that means it will not fit in doon. Okay, hold on guys. Okay. So for your fourth shell, we have two electron. Oh, sorry. Two electron can fit in your spherical orbital, and then 6 electron can fit in your P. So that is 6 electron for P. 10 electron for your D. Right? And for your F, we have 14 electron for your F. So that means 2 plus 6 is 8 plus 18. I plus 10 is 18. And then we have plus 14, 18 plus 14. That will be 32 electron in total can fit in your shell number 4. Okay, I hope you follow by this one. Okay, so I may have to rewrite I may have to rewrite this electron configuration, but yeah, I'm sorry about that noise. So let's move forward because in our electron configuration we have actually 3 rules. Okay, It is more specific on other books, but let's dive in on this. Given rule number one, orbitals fill in the order of increasing energy from lowest to highest for elements in the first three periods in order. So that's why I'm discussing this order. I have given you mnemonics for those, as I've said, for those Filipino, for those non-Filipino who can't understand the concept of that mnemonics, you may want to create your own. But si Susan pumasok sa pinto is my go-to mnemonics because I can remember it that way. But if you have other mnemonics, that is good as well. So that mnemonics that I gave you just a while ago, is an example of your rule number one, or fits this rule number one. Meaning to say, it should go on the same order. No matter what happened, you should follow that order in filling in before you jump. You fill these two electron on your spherical orbital first before you jump into your fifth spherical orbital. Okay, so that's rule number one. For your rule number two, each orbital can hold up to two electron with spin paired. So with four electron, the 1s and 2s orbital are filled and are written as 1s2, 2s2. Okay? Oh, okay. So, what does that mean? So, remember that for every orbital, say for example, this, let's go on our s orbital first. Okay, so or on our s orbital, okay, it can fit in two electron. Now, this electron should move in a clockwise and counterclockwise movement. Okay, that's why in every orbital it can fit two electrons for each. So we'll best describe this on another configuration or another way of writing, or this orbital box diagram. But before we dive deeper no, on that, let's first discuss this one. On our rule number two, it means that for every orbital it can hold up to two electron each. How about your p orbital? You mean, ma'am, you have six electron on your p orbital, but it contradicts what you have said, that each orbital can hold up to two electron with different spin, counterclockwise and clockwise. How would you explain that? For your p orbital, okay, for your p orbital, no, it has px, py, and pz. So that is an orientation of your dumbbell-shaped orbital in which it shows the movement of your electron. So let's discuss that further. But know that for every orbital, it can shows two electron for every orbital, for every orbital. So we will understand that further, no? Once we have understand yung ating orbital box diagram later. So the energy level for orbital through the third shell. This is the principal energy level orbital. And we have your 1s, 2s, and 2p orbitals. Orbitals have definite shape and orientation in space. So this one is your s. This one, of course, is bigger. This is your 2s. This one is your p orbital. No, and if you'll notice to your p orbital, it has different orientation. Okay, so as you may notice, on this p orbital, we have different orientation right here. We have the x, we have the y, and we have this z. Considering that this is a 3D model, you'll notice that this is oriented according to its 3D molecular positions. No? So on your what I've just told you about the spins, no, and the movement of electron, they shouldn't go on a similar spin, as every orbital has their two electron moving on a different spin for each orbital. So that means, no, the pairing of electrons. So a spinning electron generates a tiny magnetic field. When their tiny magnetic fields are aligned, the electron spins are paired. So the rule number three is when there is a set of orbitals or equal energy, each orbital become half filled before any of them become completely filled. So I think I should discuss this orbital box diagram, and actually this should be the first one to be discussed before that rule, because that rule is mostly or can be better understood through this orbital box diagram. So let's discuss this orbital box diagram, and let's get through each rule and how it is being applied on this orbital box diagram. So a box represents an orbital. Okay, so every orbit is this box. So there's no limitation whether be it's a sphere or on P or D or F. Let's just show it on its simplest form, which is a box. An arrow represents an electron, and as you'll notice, for each box, there are two electrons with different or with up and down arrow. For up and down arrow, it means the position or the movement of each electron per orbital, which is two for every orbital, as we have discussed just a while ago. So, a pair of arrows with heads in opposite direction represents a pair of electrons with paired spins. So, example, carbon. And we might remember that carbon has an atomic number of 6. That means we have atomic number, atomic number, let me just refresh your memory, is equivalent to the number of proton. And since the number of proton is the positively charged molecule, it should always be equivalent to the number also of your electron. Okay, so the atomic number is equivalent also to your electron. I'm going to refresh your memories. We also have your mass number discussed just a while ago. And if we are going to remember, mass number is proton plus neutron, or the sum of your proton and neutron. We will be using the atomic number because it's also the number of proton and also the number of electron. But right here, since we are talking about the cloud, the orbital, the shells, we are talking about the electron part or the outer shell part, no, that is responsible for bonding from one atom to another. So on this carbon, as we know, have six has six atomic number. Therefore, it has six proton and also six electron. Okay. So if I'm going to draw the electron configuration, will follow according to your rule number one. Okay, according to your rule number one, orbitals fill in order of increasing energy. So we'll go first with 1s, and you may remember that on S, it is just a sphere and it can fit into electron, right? So we're just going to draw a box, not a complicated spherical shape. No? And then what's next for your, not what's next for your electron configuration? Then you'll go with another S, and then the next one, what's the next one? S, then we have P. And since P can fit in 6, you'll draw a box, okay, that contains 3. Because it contains how many? It can contain, or the maximum number of electrons it can contain is 6. But we have only 6 electrons to be used or to be added in this box. Okay, so the first shell is our 1s, correct? The second one is our 2s. And the third one, is our 2p. So I'm going to expand this one. This is 2py, 2px, sorry, 2px, 2py, and 2pz. But you can just simplify it as 2p. Now we know that it can fit 6 electron. Okay, so on your rule number one, we're done with that. We followed according to the increasing energy number on our electron configuration. For number two, each orbital can hold up to 2 electron with spin paired. So before we head to this number two rule, that it should have different movement or orbital, we first see rule number three, which is when there is a set of orbitals of equal energy, each orbital becomes half filled before any of them becomes completely filled. So let me show you that. Since we have 6 electrons for your carbon, we'll first fill the first orbital box, which is 1, then 2. That's the electron, remember. The movement, the arrows that I'm adding for each orbital is the electron. So how many more? 2 minus 6, we still have 4, right? So 1 and then 2. Okay, now we have 4 arrows, so 2 more. Then we have 1, then 2. Okay, why didn't I fill the first box? Because according to your rule number 3, when there is a set of orbital of equal energy, having 2p as an equal energy, you first fill, no, orbital becomes half filled first before any of them. So you have to complete adding every orbital or every space of this 2p first before you add the second arrow. However, we are limited because our carbon has only 6 electron, which is already this one. We have 1s, 2s, and your we have 1s, 2s, and your 2 electron on your 2p orbital. Why is this important? Let me show you on our periodic table. I hope it can be zoomed, no? Whenever you view this on YouTube. But if I'm going to check the electron configuration of this carbon, you can check this on this application. Okay? We have 1s. So this means if your orbital is filled with an electron, you just add how many electrons are included per orbital. So this one contains 2 electrons, so this means 2. This one's also 2. This one has 2 electrons, so that means 2p 2. If I'm going to compare this one with this electron configuration, we are correct, right? 1s2, 2s2, and 2p2. So you can say that the electron configuration of your C6 is 1s2, 2s2, then 2p. Okay, let's try with another example. This time with say for example aluminum. Aluminum. Okay, aluminum is 13. Okay, so let's try to look or create its orbital box diagram first before we create the electron configuration. Okay, sorry, I have to move. It might not fit in. Okay, so we have aluminum, which is 13, right? So let's head back to our periodic table, or so to our electron configuration. So we have 13 that we have to fit in. So if 1s, we have 2 plus 2, we have 4, plus 3, plus 6, we have 8, plus 2 again, sphere is 2, that is 10, plus p, which is 6, that's 16, right? I think we will end up with 3p, right? Because 2 plus 2, 4 plus 6, 10 plus 2, 12 plus 6, that's 18. Sorry, is that correct? 12 plus 6 is 18, yes. So I think we'll stop with 3p. Am I doing my math correct? Sorry. S is 2 plus 2, 4 plus 6 is 10, plus 2, 12 plus 6 is 18, right? So we'll end up with 3p. So remember that 1s, 2s, 2p, 3s, and 3p. Okay? Let's rewrite that. Did you get that? Now, I hope you're understanding or you're following. For 13, we have first. You can write them down so you'll remember it easily. Then we have 2s. Then we have 2p. So for p, we have this. Then we have 3s. This one is 2p. Then this one is 3s. And then we have 3p, right? This one is 3p. So let's fill them up with the 13 electron that aluminum have. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, so we have these are 2, these are 2, this is 2, 4, 6. So 2p6, this is 2, this one is 1. So we can write the electron configuration for aluminum as 1s2, 2s2, 2p6, 3s2, and then 3p1. Okay, let's recheck it to the electron configuration for your aluminum. We have, okay, 1s2, 2s2, 2p6, 3s2, and then 3p1. Okay, if you want to practice more, you can just give or download this app, no? Then try to draw on your own. Say for example, iron. We have 26, and then recheck on this app if you've done it correctly. Okay, so that's it. That's how we write our electron configuration. I'm gonna close this down. So we have this expanded form. The expanded one includes the x, y, and z. Okay, but as you've noticed, no, we didn't fill we didn't fill the Z. So we just write the X and Y and the number of electron that is included in that orbit. Okay, so the condensed one, just write 2p2. Okay, so for noble gas notation, another example of how you write your electron configuration, the symbol of the noble gas immediately preceding the particular atom indicates the electron configuration, all filled shells. Okay, so this is a shortcut for writing them down. So let's once again open our periodic table. Okay, again, where is our noble gases? Here, it's on the column 18. We have helium, neon, argon, krypton. As I've said, they are inert and they have more stable configuration. Okay, that's why you can use them as a shortcut. Say for example, helium has two electron, right? Okay, two atomic number, that means two proton, two electron. Okay, if you're going to look at its electron configuration, it's just one s2. Okay, so for our carbon, instead of writing this part, since it's the same with with helium, you can just write with an open and close parenthesis, write your helium because helium has one s2 electron configuration, and then you'll continue to write 2s2 and 2p2. You will not appreciate it much if we're just going to write one s2, but it is really helpful for elements that includes argon, krypton, or the elements below them. So let's have an example on our aluminum. So aluminum, okay, for aluminum, we're going to look at the the noble gases before the period of aluminum, right? That's not argon, that's after or that's in line with aluminum. So we have to look at before aluminum. So that the noble gas before aluminum is neon. Okay, now, neon right here has 10 atomic number or 10 proton or 10 electron, right? So, um, enable for us to not write the 10 part, which is this one right here, right? 2s2, 2 plus 2 plus 6 is 10. This one is equivalent to your 10. If we're going to look at neon, this is also the electron configuration of your neon, right? I hope you are following, guys. You can pause this video to digest everything down if you're having a hard time understanding it. You can ask anything on the comment section as well. Where's the neon electron configuration? Hold on. I'm sorry. Okay. Here's the neon electron configuration. You have 1s2, 2s2, and 2p6. Okay, so for you to not write that long electron configuration for aluminum, we will just take this neon because it's the noble gas before aluminum. So that is close and open bracket. Then we have neon. That means this electron configuration, okay, right here, this electron configuration right here, now is equivalent to our neon. So that means neon, then write the remaining one, 3s2, 3p1. Okay, if we're going to look at aluminum, again, you can practice in your home. You can just check here on this application. It's a very good app. But if you have another application that's better than this one, let me know in the comment box. We have this neon, right? We right neon, 3s2, and then 3p1. So we are right on our noble gas notation. We're also right on our electron configuration, yung orbital diagram one. Okay? Okay. So that's it for our electron configuration writing. No? We'll move forward to our valence shell. So what is the valence shell? So this is the outermost incomplete shell. You will not see this mostly in our noble gases. You'll notice this on your 8A or the 18th column on your application. Helium is already complete. If you're going to go back to this electron configuration, the first shell, which is 1s, is already complete. You know? Uh, or what is an incomplete one? Let me show you. This one is an example. This carbon right here is an incomplete one, right? Why? Because we have an empty space on its orbital. But we have this so-called octet rule. Okay? On our octet rule, okay, say for example on our carbon, remember that carbon has 6 electrons. And the first shell is 2s, right? Sorry, the first shell is 1s. And that can contain 2 electrons, correct? Okay. The rest, yeah, so we have 2 electron right here, which is a stable version of your helium. We will not count it over. So 2 minus 6 is 4. We still have 4 electron on its outer shell. So an octet rule state that for every shell, it should contain 8 electron. Okay? So this 4 shell is what we will be using in computing. Okay. So on octet rule, it says for every next shell, the first one is 2, then the rest would be 8. It would not apply to all, but this is a general standard, okay? So this is what we call valence shell. The valence shell is the outer shell that is not complete to 8. So that means in carbon that has 6 electron, the first one is 2, right? And then 2 minus 6 will be 4. We have 4 on our outer shell, which needs 4 more electrons. That's why in organic chemistry, we will notice that carbon can combine or can connect to 4 more atom because it needs 4 more electron for its outer shell to be completed. So valence electron is an electron in the valence shell or outer shell. So this structure or this forming, the one you see in this table 2.8, is what we call a Lewis dot structure. So the symbol of an element represents the nucleus and the filled shell. So for your 1A, you have H. I'll give you another example of this octet rule. Okay, so let's use, say, for example, I'm going to open up my periodic table once again. I'm sorry about that. Let's use nitrogen, say, for example. So for nitrogen, we have an atomic number of 7. So that's N and then 7. So on your first shell, you have 1s2, right? So let's remove the electron configuration so that it will be easier for us. On our first shell, that's 2. Okay? On our second shell, that's 2 minus 7 is 5. Okay, we can fit in up to 8 on our second shell. So we have 5, no? How many more for us to be stable? We have 5 minus 8 because every next shell after the 2 is or should contain 8 for it to be stable. So for your second shell, you have 8 minus 5. You still need 3. That's why there are how many available bond spots on your nitrogen? No, we have 3. It can still bond up to 3 atom. Okay? So you'll understand this more on your organic chemistry, but that's how your valence shell electron work. Why did I say before that your noble gases are already stable? So see, for example, we have your neon right here. Neon contains how many? 10 atomic number, 10 electron, 10 proton, correct? So when we go to your octet rule and follow the valence shell electron configuration, the first one should be 2, right? 2 minus 10 is 8. Remember, for you to be stable, you should have 8 electron next to your 2, or the next succeeding shell should have 8 electron each. So for this, neon already have 8 electron. That's why it doesn't need any compound, no, or any atom for it to be filled. That's why neon doesn't react that easily to other atoms. It's a stable gas. Okay? So that goes the same for argon. If you would like to try it at home. Krypton, xenon, radon, and your helium, they are all the same. They always have 8 at its outer shell. Okay? But for the rest, they will always have, or they have the need for another electron, so they need something to bond it. Okay? The remaining or outer shell of it. So this one is an electron configuration and periodic table. This one is the main group element on the S block. This one is F block. This one is P block. And this one, last one, is the P block. Okay. So next is our electron configuration notation with Lewis structure. Okay, we're done with this. We are done with noble gas notation, Lewis dot notation, and then we'll go back to our periodic property. This is what we are discussing just a while ago, right? Can you still remember the periodicity, the trend that I'm talking about? So as we have seen, the periodic table was constructed the basis of trends or yung periodicity in chemical properties. So with an understanding of electron configuration, chemists realized that the periodicity of chemical properties could be understood in terms of periodicity in electron configuration. So, to sum it all, now we look at the periodic properties, atomic size, ionization energy, electron negativity, and also electron affinity. Okay? Okay, so next tayo. Oh, wow. Okay. So for your atomic size of an atom, it is determined by the radius it's out of its outermost occupied orbital. So example, the radius of chlorine atom is 99 picometer, which is determined by the size of its 3p orbital. The radius of the carbon atom is 77 picometer. That is determined by the size of its 3 2p orbital. Don't worry, you will not memorize every picometer or every radius or atomic size. What's important is you know which is which will have bigger atomic size or greater atomic size. No, well, it's easy if you know your periodic trends. If you're going to look at your periodic table, you'll notice which among them is bigger. As you've noticed, this one is your group 1A, and as it goes down, the trend in your periodic table, it becomes bigger. Okay? And it's from uh, from left to right, it becomes smaller. You can create a table for this one so you will memorize this easily, the trends, no? So we have um we have we have top to down, and we have left to right. Okay, you just have to create a table. Then the first one is your atomic size, okay? Atomic size. So what's the trend for your atomic size from top to bottom, top to down, it increases. From left to right, it decreases, right? Let me know if I'm creating, if I'm correct, sorry. How about the ionization energy? Okay. So the energy required to remove the most loosely held electron from an atom in the gaseous state. So what's the trend for ionization energy from let's create a uniform one, no? This one kasi is from bottom to top. So let's follow this one so it will be uniform. Top to bottom or top to down. Okay, in general, it increases across the row, so it increases from left to right. Okay. Okay. And in the same shell and subject to increasing attraction as the number of proton in the nucleus increases. So it increases going up a column. So that means it decreases going down, right? Let me know if that's correct. Okay, so that's it. That's the trend for your ionization energy. Before we end this, I would like to add electron negativity. Electron, oh, sorry, electron negativity. Okay, let me give you just also a periodic table. The most this question might be asked, might be not, I don't know. But the most electronegative atom that we have is fluorine. Now take note of that. Okay, so the most electronegative atom is fluorine, and that is 3.98. Okay, so if we're going to look at it, chlorine can be found on your rightmost part of your periodic table. So it's safe to say, as a general rule, say for example, you really don't know how to answer the exam. Now from left to right, it goes or it increases. Okay, and from top to bottom. Okay, so your electronegativity from top to bottom decreases. Okay, this one is decreases. If you're going to check just this once, fluorine is the most electronegative atom. That means it's higher than fluorine, it's higher than bromine and iodine. So it's safe to say that from top to bottom, the electronegativity also decreases. Now, for your electron affinity, I don't know if it will be discussed in your book. No, some just discuss atomic size, ionization, boiling and melting. You can write down boiling point, melting point, right here. It's up to you how long are you going to write your periodicity. But this first four is the most important one. So for your electron affinity, remember that from top to bottom it decreases, and from left to right it increases. Okay, so for your boiling point, melting point, I think there's a lot of exception on this one. And it's hard to write a general rule, but if you wanted to add notes for this table, it can really help you in your exam for you to remember and memorize them all. So just please add them out, okay? Add them down. So I think that's it for our discussion of your atoms. Thank you so much for listening, and I hope you ace your exams.